Welcome back to this new episode of the course on computer vision. Today, as usual, we will continue discussing the diagram that describes a vision-based measurement system. After talking about the camera and the optical system, today we'll focus on another very important element of our system, lighting. If we think about the general layout of a measurement system, we can consider the illuminator as part of the conditioning block. In fact, thanks to lighting, it's possible to somehow enhance the light information that enters the camera and hits the sensor. This way, the resulting image will be optimal. But at this point, what does it mean to have an optimal image? When we talk about vision-based measurement systems, having an optimal image means having optimal contrast. Contrast, as the word suggests, is the difference within the image between light and dark tones. So, having a very light object on a very dark background means having good contrast. On the other hand, having an object that's the same color or brightness as the background means having zero contrast. The goals of a good vision-based measurement system are directly tied to this parameter, contrast. A good lighting system, in fact, should maximize contrast in the areas where I need to measure, minimize it where I don't need to measure, and make the whole system robust. So, it should ensure that the contrast doesn't change over time. To choose a good illuminator, it's necessary to take into account several aspects related to it, including its geometry, structure, the wavelength or color of the illuminator, and whether a light filtering system is needed. In this episode, we'll analyze these aspects in detail. We'll look at each of these aspects so that you'll have the necessary tools to choose the ideal lighting system. Let's start with geometry, understood as the relationship between the object being measured, the camera, and the illuminator. We can identify 4 different types of lighting: backlight, diffuse light, bright field, and dark field. Each type has certain properties that make it better suited for specific measurement applications. In backlight or rear lighting, the illuminator points directly toward the camera, with the object being measured placed on top of it. This causes the final image to be inverted, with the object completely black and the background completely white. As you can see from the image, for example, with a backlight illuminator, the outlines of the captured objects are very well defined and the contrast is extremely high. On the other hand, all information related to the surface of the object itself is lost. In diffuse lighting, on the contrary, the light is directed toward the object and not toward the camera. In this case, the light is multidirectional, so it hits the object from many directions. In this case, this type of light is the most common. In fact, all the ceiling lights you have at home use diffuse lighting. Why is it common? Because usually, this type of lighting always provides a good compromise in terms of contrast, even if it might not be the ideal solution. As you can see in the sample image, which was taken with diffuse lighting, the object is generally well lit. In this case, the goal was to identify the chips along the edges of the glass jar. Here, the goal was achieved because, in fact, it is visible. There's enough contrast to let us see the chip exactly. However, it's very likely that it would have been possible to choose an optimal illuminator that would have further improved the contrast, different from diffuse lighting. Let's continue by defining the third type of lighting, bright field or bright field illumination. In this type of lighting, the light is unidirectional and directed toward the object, with high angles of incidence. That is, the angles between the work surface and the illuminator are very steep. So, in practice, the illuminator is placed very close to the camera. This is the typical concentrated lighting, where most of the light is focused on a single point, on a single area of the object to be captured. Very similar in concept, but different in result, is dark field illumination. In dark field, just like in bright field, the light is unidirectional and directed toward the object. In this case, however, the angle of incidence is very low. And this means that most of the light emitted by the emitter hits the object. And then it goes away and doesn't hit the camera. The camera's pixels, on the other hand, will be hit if there are surface irregularities or defects on the object. So, by comparing these last two types of lighting, we see that bright field is used to illuminate specific parts of the object very well. Dark field, on the other hand, is used to illuminate very well the areas where there are defects. In the example, this effect is very clear. In the image, obtained using bright field illumination on the left, you can see how the object is well captured and with good contrast. In this case, it was a microscope slide. In the image on the right, instead, obtained using dark field illumination, the object appears much darker, while the defect present on the slide glass is clearly visible. With backlight illumination, you can achieve excellent contrast on the edges of the object being measured, thanks to the negative image. With diffused light illumination, you can almost always get good contrast, even if it might not be optimal, and it's used for objects with surfaces that have different textures, angles, and so on. Bright field illumination is used when I want to brightly light up a specific area of the scene and improve the contrast there. But be careful, because if I overdo it with the light, I create overexposed areas, which means everything turns white and the contrast is lost. Finally, dark field illumination is excellent for identifying defects on the surface of the object being measured, because with its low angles of incidence, it ensures that light is only scattered in areas where there are surface discontinuities. Having looked at the geometric properties of light, let's move on to discuss the second characteristic of illuminators, wavelength or color. In fact, different types of illuminator can produce light with different wavelengths and therefore different colors. From ultraviolet to visible to infrared. It's very important to keep this characteristic in mind because, depending on the light that hits the object, I might get different types of images. Let's look at an example. Let's imagine that what we're measuring are these 4 candies, each wrapped in a different colored paper on a light blue background. If we try to illuminate these objects with illuminators of different colors, for example, using red light or blue light, you can see how the resulting image changes. In the first case, with red light, the candies with red and yellow wrappers appear lighter, while the others look darker. In the second case, with blue light, the candy with the blue wrapper is slightly lighter, as is the background. This happens because, generally speaking, objects that are the same color as the light reflect more, and therefore appear lighter in the image. On the other hand, objects with opposite colors reflect less light and therefore appear darker. When I say opposites, I'm referring to the color wheel you see here on the left. Since the goal is always to have the highest possible contrast, you can see how the example with the red illuminator is optimal for recognizing blue and green candies, because in this case the contrast between the candies being measured is maximized, and the background is maximized. Now let's talk about polarized light filtering. Polarized light is light made up of electromagnetic radiation that oscillates on a specific plane. Unpolarized light, on the other hand, is made up of radiation that oscillates on different planes. In many cases, it's convenient to use a polarizing filter that blocks polarized light, because this way we can further improve the final image. When unpolarized light hits an object, part of the reflected light will be polarized along a specific direction. Now, if I place the polarizing filter, that is, a filter capable of blocking polarized light between the reflected light and the camera sensor, I'll be able to eliminate the effect of this light. This will result in an image that is generally darker, thus avoiding overexposed areas, which would otherwise lead to increased contrast. Still nothing. Let's explain the effect better with another example. In the images you see here, this is very clear. At the top, in fact, you can see that too much reflected light creates completely white areas, making them unusable for taking measurements. By applying a polarizing filter, the reflection is reduced and the areas that were previously white become visible again and therefore measurable. To be clear, this is the same effect you get when you use polarized sunglasses, which filter sunlight reflections better because they block the part of reflected light that is also polarized. Let's now summarize everything we've discussed. A good lighting system is essential for getting good images, meaning images with excellent contrast and a high difference between light and dark tones. The lighting system ensures robustness against external disturbances, such as changes in brightness, for example. This way, I can be sure that the contrast always remains consistent. Depending on the measurement you want to perform, it's necessary to choose the most suitable lighting system, since you always have to keep this in mind. What do I want to measure before choosing the best illuminator? Finally, to choose the optimal illuminator, it's important to consider all the properties of the lighting system, such as geometry, type, color, and any need for filtering. Today we saw how even the illuminator is very important for our vision system. At this point, we can move on to the last remaining element, the one that will actually allow us to perform the real measurement, the image analysis software.